Hello, am I audible? I think I'm audible. Hello, hello. I should be audible. Hello, am I audible? I'm audible. Okay. I think we can start now. Okay, so in today's class, we are going to discuss about some of the discretization scheme that I have missed previously. And also we are going to discuss about how the discretization goes on in case of unstructured trade. So uh, let us start. I think most of the people have joined the class. So this one. Yes. So there is one scheme which is called the exponential scheme. So there are multiple schemes that I have actually told you, uh, like the quick scheme and the central difference scheme, the point scheme itself. So today we are going to discuss about the exponential scheme and the hybrid scheme itself. And we are also going to see the false diffusion in case of our point scheme. And we are also going to see how the discretization goes on in case of an unstructured tree. So going to the exponential scheme itself, exponential scheme. So the proposal is based on the exact solution of the convection diffusion equation, the heat convection diffusion, that 1D heat convection diffusion equation. The proposal is based on 1D heat convection diffusion equation. Okay, so we know that if I actually go to the general transport equation itself, so we know that ddx of rho u phi is basically equal to ddx of gamma d phi dx. Okay, so over the domain, so then let us define the Peclet number to be equal to that of rho u L by gamma, where rho is the density of the liquid or the gas which is flowing in the domain itself. It's a convection diffusion equation, and the convection of the fluid which is going from one point to another point, and which is also kind of followed by diffusion. And u is the velocity, and L is the length of the domain, and gamma is basically your the diffusion coefficient. Okay. So the exact solution of this equation, this one can be written as phi x. If you solve this differential equation, you will get it to be like phi x naught plus phi of L minus of phi L phi naught, and which is exponential of Peclet number h by L minus 1, exponential of Peclet number minus 1. So that's how it looks like. So therefore, if I actually consider the Peclet number itself, it's basically the ratio of the convective to the diffusion process itself. And if I actually plot the Peclet number, this phi L as a at x equal to, which is changing from x equal to 0 to x equal to L along that order itself, for different values of Peclet number, if I plot it, so if Peclet number is basically equal to 0, then it is actually if it is actually equal to that of 0, so then it becomes a linear line, but a linear line, Peclet number equal to 0. So if Peclet number is positive, the curves actually move downwards. So Peclet number is positive. If it is very, very positive, it actually moves like this. Peclet number very, very greater than zero. And if Peclet number is less than zero, it will kind of move upwards. And if Peclet number is basically uh, very, very less than zero, it will be like this. So depending upon the Peclet number itself, the nature of the curve itself, that is a profile along the length of the rod that will change. So x equal to L by 2, it will change. Okay. So that's how it works. So if Peclet number is basically equal to zero, that means it's a pure diffusion process. Diffusion process. So if it's a pure diffusion process, we always know that the conduction itself is a linear line. So I've actually showed you the profile with pure conduction and also with conduction with source term. So if there is a source term, it actually becomes parabolic and it tends to go toward unboundedness. And if it's equal to zero, then it becomes a linear line. So if Peclet number is very, very greater than zero, so phi x is basically equal to phi naught. So this phi naught and phi L are basically the temperature at the both end at s equal to 0 and x equal to L itself. And if Peclet number is very, very less than 0, then phi x is basically equal to phi L. Okay. So at x equal to L by 2. So what you can do is basically you can change the Peclet number and then you can plot the profile by using MATLAB or Octave, and then you can see that how the profile changes. And the slope of the profile, whether it's a concave or a convex one, it actually you can see it from that of the double derivative of the curve itself, the double derivative of the function. So from there you can basically find it out that whether that will be a convex one or a concave one. So that's how it works. So one thing we can do is basically we already know that the exponential profile is this one. So one thing we can do is basically we can put it directly in the discretization equation itself, or we can we can basically put it in the governing equation, put it in the general transport equation, general transport equation, and discretize it, discretize it, and then find the phi profile. So since we are actually directly are able to find out the value of x and then kind of discretizing that by putting that in the general transport equation, we are kind of getting more accurate profile. And it's always not the case that we are going to see an exponential variation. It's a very typical case. So this exponential scheme, if it's kind of exponential, the solution is tending towards exponential in nature, and we can consider this kind of discretization. Otherwise, that is, we are going to avoid this kind of discretization. Generally, we go for this quick or hybrid scheme, or we go for this affine scheme central difference. Those are the schemes we generally prefer. But in this case itself, since we know the solution to be an exponential one, so we are considering discretizing the general transport equation by assuming the profile to be an exponential one. So therefore, the analytical solution we already know is phi equals to phi p plus phi e minus phi p exponential of e of x delta x e e minus 1 divided by exponential of p. This is Peclet number. So you can write it with p subscript e minus 1. So if I actually draw the domain again, so this is capital P, this is capital E, and this is capital W. And this is small w, and this is small e. And then we are considering a control volume like this. And then this is delta x wt, and this is delta x EP or PE, so which we have already written here. So this delta X WP and delta X PE is basically since the same, since we are considering it to be a uniform grid. So uniform grid basically means these are some terminologies we generally use in CFD. So uniform grid is, for example, you are considering a domain like this, and then we are dividing the domain into equal delta X. So then we call it to be an uniform grid. So delta X is same for all control volume, for all control volume. But that is not the case in most of the cases. Since, for example, if that thing is basically flow through a pipe, and this one is a flow through a pipe, and then we have a parabolic velocity profile. And if I want to do CFD for it, so what I will do is basically in case of central difference also, we assume the profile to be a linear one. But if I actually near this wall region itself, if I kind of magnify this, I will see that this is parabolic in nature. Okay, but if I actually consider that to be a linear one, so this is the error or the mass imbalance I'm going to get. So this is actually one of the things which is undesirable in our case. So then we can do is basically this linear function can be assumed to be an overlap of this quadratic function can be assumed to be an overlap of uh, linear function, linear lines. So like this. So if I actually take the cell to be a very small one near the wall region, so this quadratic profile can be kind of assumed to be a combination of linear lines. So for example, if y is basically equal to ax square plus ax, if my profile is somewhat like this, so if x is very small, then y actually becomes proportional to ax. So that's what I'm saying. So then we can assume the profile to be a linear one, similar to the central difference in V2. So in order to make so what we are doing is actually in order to assume the profile to be a linear one, we are basically refining the cell in the near wall region or the region where the gradients are basically very high. Okay. But in the center region, the gradients are basically not so high. So there we can consider the cells to be a larger one because there the gradient actually decreases in the center line of the pipe itself, and obviously in the middle the gradient is uh, this is equal to du dy equal to 0 since that's a maximum. So therefore, we can assume the cells to be a larger one here in the center of the pipeline, and therefore the cells is larger in the center of the pipeline. But as you go towards the wall region, the cell size actually decreases. So this is called non-uniform cell because then delta x actually becomes a function of y uh, instead of being constant. Okay, instead of being constant, it becomes a function of y, and therefore we actually have to change the code accordingly. So this is also known as biasing in different solvers like ANSYS Fluent. So they will ask for something which is called the bias factor itself in order to find the ratio between the largest and the smallest cell size. So those things, and also ask for the growth rate also. So those things actually should be taken into account. So by reading the user manual, you can know that whether so what are the parameters or how you should tune the parameters in order to get a uh, legible solution. Okay. So coming back to the exponential scheme itself. Uh, so this, uh, if I actually go to this part, so phi is basically equal to phi p plus phi minus phi p exponential of particular number x divided by delta x p minus of 1 divided by exponential of p minus 1. So here, so it is at point p, or here, so this is not at point p, but here x equal to 0 at point p. Okay. And For example, if I consider x equal to 0 at W, so if I actually draw the control volume again, so this is like the control volume itself. This is small w, this is small e. This is capital P, this is capital E, and this is capital W. Okay. Uh, so small w and small e are basically the cell faces itself, the common face between the capital W and the capital P cell, and where small is cell face between the capital P and the capital E cell face. And this capital W, capital P, and capital E are basically the cell centroids for the waste cell face, the cell centroid of the cell of my interest, which is capital P, and capital E is basically the east cell centroid, east cell centroid. Okay, this one is west cell centroid, and this is my uh, uh, my trace cell centroid of control volume of my interest, for which I'm writing the equation. Okay, so if x equal to 0 at capital W, then this can be written as phi equals to phi W plus phi P minus phi W exponential of PW x, so delta x WP minus 1 divided by exponential of PW minus 1. So PW and PE are I'm writing because if the Peclet number changes along the domain itself, so it's a padding density or the padding diffusivity kind of a domain. So that's why I'm writing this equation in that manner. So Peclet number small w is basically equal to rho u small w divided by gamma w divided by delta x w. So this kind of nomenclature I've already used. So this actually becomes fw divided by gamma w by delta x wp. Okay. So now let us go to the governing equation. So I have written how the variable actually can be expressed similar to that of the analytical solution. So now let us go to the governing equation. So governing equation is what? Rho u phi. So this is after reduction from the general transport equation, which I am not showing, or which I have shown you multiple times, minus of rho u phi minus of gamma d phi dx small w equal to 0. Okay. So this one is basically capital P, this is capital E, and this is capital W. And as you all know that this is small w, this is small e, and your x equal to 0 starts from here, and the x actually goes to be positive in the right hand side direction, whereas it is negative when it goes to the left hand side direction. Okay, so then phi is basically equal to phi p plus phi e minus phi p exponential of e e x by delta x e minus 1 divided by exponential of e minus 1. And then phi small is basically what? Phi p plus phi e minus phi p. Peclet number divided by 2, since my x actually becomes to be like delta x divided by 2. Okay, since I'm going to be delta x by 2 distance right hand side from the point P itself, so it becomes Peclet number divided by 2 minus 1 by Peclet number minus 1. Okay, is it clear to all of you? This is at point E. Is it clear to all of you? Hello. Hello. So now going to that of the phi small e itself. So phi small e is basically equal to phi p plus phi minus phi p exponential of Peclet number divided by 2 minus divided by exponential of Peclet number minus 1. So now rho u phi e minus of gamma to d phi dx e. So now I also have to find out the derivative of the phi variable, which I know the nature of the variable from this exponential assumption that I'm doing in my case. So this is phi fe phi p plus phi e minus phi p exponential of Peclet number divided by 2 divided by exponential of Peclet number minus 1. So that's what I'm doing. Minus of gamma e. So this is going to be phi e minus phi p divided by exponential of Peclet number minus 1 exponential of exponential of Peclet number minus 1 exponential of Peclet number divided by 2, and then going to the derivative of, so this is Fe delta x e e divided by a, delta x p divided by delta x p gamma. So it becomes Fe by gamma, becomes Fe, and the gamma cancels out from front, so it becomes Fe. So this becomes Fe. So now we can reduce the equation further. So this is Fe phi p plus Fe phi e minus phi p exponential of Peclet number divided by 2 minus 1 exponential of Peclet number minus 1 minus phi e minus phi. That is already done. I don't repeat it. I can simplify it further.
Sir, this Fe is indicating what?
Fe basically means rho e. So rho is the density and u is the velocity. So at the E surface itself. So this is kg per meter cube multiplied by meter per second. That is mass flux. Okay. So if E phi p exponential of Peclet number minus of F phi p, okay, plus of. So one other thing is you actually requested that the assignments which are yet to be submitted that should be discussed by me. But I asked for the assignments to be given to me in the chat box, but no one actually gave it to me. Okay, they have not given it to me. That's why I'm unable. So if you want me to discuss a thing, you should either you email me the assignments or you actually put that in the chat box so that I can go through it and then I can discuss in the next class. So if E phi E minus of if E phi P exponential of Peclet number divided by 2 minus 1 minus of if E phi E and this exponential of Peclet number divided by 2 plus of if phi P exponential Peclet number divided by 2 exponential of Peclet number minus 1. And then this can be simplified further. So which will result in Fe phi p exponential of Peclet number minus of Fe phi e exponential of Peclet number minus 1. Okay. So then I can go further if I consider, so this will be like rho u phi e minus of gamma d phi dx e equals to if e phi p plus phi p minus phi e exponential of Peclet number minus 1. Okay. So since we already know that we have to do this kind of thing for the west face also, so it will be similarly like if we derive it, it will be like Ep phi p plus phi p minus phi e divided by exponential of Peclet number minus 1 minus of f w phi w plus phi w minus phi t exponential of pw minus 1 equal to 0. So therefore, which can be further rearranged. So it will be like Fe plus Fe divided by exponential of Peclet number minus 1 plus of Fw by exponential of Pw minus 1. And then this is phi p, and this is equal to Fw plus Fw divided by exponential of Peclet Pw minus 1 phi w plus Fe exponential of e minus 1 phi e. And then this can be further reduced to Fw by exponential of Pw minus 1 plus Fw plus Fe exponential of Pe minus 1 plus Fe minus Fw, and this can be phi w phi p equals to Fw exponential of Pw exponential of Pw minus 1 phi w plus Fe exponential of e minus 1 phi. And therefore, we can also write this equation like Ep phi p equals to Aw phi w plus A phi e. So this kind of writing is basically very much useful when you are going for programming these equations. So therefore, this one is basically equal to that of this Aw is basically equal to this one. Let me color it with different color. So this one, and this is with this one, and this is with this one. Okay. So conservativeness is already maintained. So if we actually use exponential for the east and the west phase, you will see the conservation is maintained. Boundedness itself is maintained because since this one is without a source term itself. And going to the accuracy itself, so from the graph itself, you can also see that this one is already bounded since the middle value is not greater than both the values itself. In extreme cases, it can go to the higher value, but not greater than that at the higher value at the other end of the rod itself. So you can see from the graph also whether it's bounded or not. And going to the accuracy itself, so this accuracy is basically exact for 1D. So typically you don't have any accuracy problems since you are actually used for the since you are using this for that of the exact solution for the discretization itself. But this is actually one of the scheme we don't do it. So one of the fundamental reason behind it is that it is expensive to calculate the exponentials. So this exponential of PW is expensive to calculate. Expensive to calculate. So then this becomes an issue. So that's why this discretization scheme, this discretization scheme is computationally expensive. Computationally expensive and expensive. So typically, since this one is computationally expensive, we generally avoid this thing. But this is actually in certain problems where convergence itself is a problem with computationally inexpensive schemes like central difference scheme or point scheme, then we should go for this kind of schemes. And if it's a 3D problem or 2D problem instead of a 3D one, for example, we have east, west, north, south, then it will be like you can calculate it to be like EP phi p equals to A in phi n plus AS phi S plus AE phi E plus AW phi W. Okay. So your general transport equation when you're writing it down, so it will be like rho E phi gamma d phi dx at east face minus of rho U phi gamma d phi dx at west face and then rho U phi minus gamma d phi dy at north face minus of rho U phi minus gamma d phi dy at south face. This is equal to 0. So then phi actually becomes a function of both x and y. Then it is basically it's a function of y when you are considering it to be in this direction. It's a function of x when you consider the heat convection diffusion in this direction. So typically by using superposition principle, you can kind of superimpose both the equations and then you can find out the equation in this format where AP, N, AS, A, and AW will be known. And therefore you can put it in a program and then you can run it. Okay. So even for 2D or 3D field, yes, Dhananjay, do you have any question?
I had one request, sir. If you can elaborate on assignment 12 to some extent, so that will be helpful for us.
देखो भाई मेरे पास असाइनमेंट नहीं है, ठीक है। मैंने बोला था चैट बॉक्स में देने के लिए, कोई नहीं दिया अभी तक, ठीक है। मैंने उसे लिख के भेजा था। इफ यू वांट द असाइनमेंट 12 टू बी एड्रेस्ड, यू सेंड मी टू द चैट बॉक्स, ठीक है। तुम भेजो, मैं देख के बता देता हूँ, ठीक है। यू शेयर योर ईमेल आईडी, आई कैन सजेस्ट यू सम सोल्यूशन, ठीक है।
Okay, sir.
पहले तुम असाइनमेंट भेजो चैट बॉक्स में, मैं देख के तुमको बता देता हूँ। तुम ईमेल आईडी नीचे लिख दो चैट बॉक्स में, मैं तुम्हें भेज
Sir,
दूंगा, ठीक है।
this chat box is at the moment is disabled, perhaps.
नहीं डिसेबल तो नहीं है, मैं तो चैट बॉक्स में टाइप करता हूँ, बाकी लोग भी टाइप करते हैं, डिसेबल तो नहीं है।
No, I'm not able to put in actually. पता नहीं.
हाँ पता नहीं, बाकी लोग तो करते हैं। देखो धनंजय
यहाँ
सर,
नहीं यहाँ नहीं हो पा रहा है, मतलब यही सेम रिक्वेस्ट आई वाज टू पुट इन चैट बॉक्स, तो आप इसलिए
देखो
मैंने
भाई
हाथ
तुम
रेस
मेल
किया
में
था.
भेजो, देखो मैं
ओके
मेल
ठीक.
भेज देता हूँ, यहाँ पर कर दो, जैसे, ठीक है। मैंने मेल भेज दिया है। आई थिंक यू आर नॉट लॉगिंग फ्रॉम द email which is registered for your NPTEL courses, and that's why you are having this issue. I don't know what's up this, but इस email ID में भेज देना, क्या
It's the
प्रॉब्लम है
same.
तो उसे इस email ID में भेज देना, मैं देख लूंगा, ठीक है।
ठीक है, it's the same email ID. ठीक है.
ठीक है, नहीं हो रहा है क्या कर सकते,
Okay.
ठीक है। So conservativeness, transportiveness, and boundedness, those are the things that I've already discussed for this case itself. So then going to that of the unstructured grid. So that's actually one of the things I want to discuss. Since for the structured grid, we know that the cell is typically like a hex cell itself. But in case of where the normals are mutually perpendicular to each other, where this one is nx and this one is ny, and if I make a dot product of it, that is basically equal to 0. So since they are mutually perpendicular to each other, that's very much easy to do. And also we are going with the uniform grid itself, where delta x is same over the whole domain. That is constant. And now we are going to the unstructured grid. So unstructured grid typically looks like this triangular grids if it's a 2D one. It looks like a tetrahedron if it's a 3D one. So these are unstructured grid. So if the grid is not Higgs grid, or if the grid is not Higgs grid, or what should I say? Quad grid for 2D, quad grid for 2D, or Higgs grid for 3D. Higgs grid मतलब rectangular parallel shift for 3D. मतलब बेसिकली 2D में ऐसा दिखेगा, और 3D में ऐसा दिखे, ऐसा ना दिखे तो समझ लेना वो अनस्ट्रक्चर्ड है, देन इट इज अनस्ट्रक्चर्ड. Okay. So then it is unstructured. So now we are going to discuss about this 2D thing itself. So how to deal with an unstructured grid. So
Sir,
after
the
that, I
one
will
which you
go.
have shown, the one which you have shown in rectangular and cubical form, agar, if this is actually structured, na, and if this is not the case, then it is unstructured. Is my understanding correct?
नहीं नहीं, ये 2D में क्वाड होना चाहिए, क्वाड्रिलेटरल टाइप का. इट शुड बी लाइक अ बॉक्स और अ रेक्टेंगल. और 3D केस में तुम्हारा जो होना चाहिए, इट शुड बी लाइक अ रेक्टेंगुलर पैरेललोपाइड. So if
This
this
is
is the case,
unstructured or
then this is
structured, you are saying?
structured.
Structured, okay. Because ये आपके
And
शायरी में शायद this is the unstructured लिखा है.
नहीं
Okay.
नहीं, मैं स्ट्रक्चर्ड
Okay.
ही लिखा हूँ. नहीं
ठीक है, ठीक है.
नहीं,
Okay, understood. Understood.
if it is not the case, then it is unstructured. Okay,
Okay, ठीक है.
वो मैंने verbally बोला था. And these
ठीक है.
cases are unstructured. Unstructured, actually, you will see that most of the people actually avoid this grid because these are typically different, difficult to converge. But if the geometry itself is a complex one, you have to go for unstructured grid. Okay, so going to the discretization on the unstructured mesh itself. So discretization of unstructured on structured. So going to the sale of my interest. So this one is my E cell. This one is my P cell. So this P is the point P itself. So this one is in1 cap. This is in3 cap and in2 cap. So in1, in2, and in3 cap are basically the normal which are perpendicular to the cell face itself, making a perpendicular angle with the cell face. And this one is delta A3, and this one is a delta A2, and this one is delta A1. As of now, we are dealing with the 2D. So this is basically a line multiplied by if the length is basically L1. So L1 multiplied by a constant within the Z direction. So L1 multiplied by W will be equal to that of delta A1, where W is basically your width normal to the paper. Okay, so it will be normal to the paper itself. So going to the equation, the general convection, the general transport equation. So it will be like PVP and then it T to T plus delta T. So this is basically ddt of rho phi dt dv equals to. So you have to integrate both with respect to the control volume and the time itself. When it's a spatial, when it consider both the spatial and the temporal terms in the Navier-Stokes equation or the general transport equation. So this one is rho v phi, and this is equal to that of control volume of P, and this is T to T plus delta T, and del dot of gamma grad phi dt dv plus dvp T to T plus delta T is dt dv. Okay, and then if I actually kind of simplify it, so the first temporal time I will integrate with respect to the time initially. So it will be like rho phi minus rho phi naught dv equals to or plus of T to T plus delta T dvt using the Gauss divergence theorem, that is n cap rho v phi dA dt prime. So this is basically equal to that of t to t plus delta t CVP n cap dot gamma grad phi dA dt prime plus the source term itself, so which will be equal to that of CVP. If the source term is kind of constant, it's kind of function of the phi itself, but not the spatial uh, variation itself. This can be written as a source term can be written as this as of t to t plus delta t AC sp phi p dt prime, since this is s dt prime dv, and we know that s delta v is basically AC plus sp phi p, and this is basically equal to that of AC plus sp phi p delta t. Okay, so now we are left with the convection and the diffusion term, so that I will show how to discretize it. So are you okay until now? Okay, so going to the discretization of that of the t to t plus delta t, and then EVP, this is basically equal to that of n cap dot rho v phi dA dt prime t to t plus delta t sigma 3 I equals to 1 in I cap dot rho v phi delta AI dt prime. So now we are considering this in cap dot rho v cap phi, assuming, or you don't have to go, you can go for that approximation later on. So going to the discretization of that of the uh, diffusion term, this is in cap dot rho cat phi d a dt prime is basically equal to t to t plus delta t, and then sigma 3 I equals to 1 in I cap dot gamma cat phi delta ai, and then dt prime. Okay, so in cap are the normal vectors, which are the vectors normal to the surface, the corresponding surface, and delta ai are basically the area of the three surface we already have. So if I redraw it, this is n3 cap, the area corresponding to this is a3, this is n1 cap, the corresponding to 1 is a1, and this is n2 cap, and corresponding to it is a2, the area a2. Okay, this one, this one, this one. Okay, so now the convection and the diffusion term will need further processing. So I've shown you that how to discretize the spatio-temporal way, the spatio-temporal terms which are present in the Navier-Stokes equation itself, or the general transport equation. But from now onwards, we will drop the time integrals, because time integrals we already know that we can easily deal with that. But as I've shown earlier, in the implicit and the explicit scheme, and therefore I will show you now that how to deal with the spatial integrals, which is actually one of the problem. So convection, diffusion, and diffusion term treatment, and to be done. Once a spatial integrals have been have been processed, time integrals can be treated using the explicit, fully implicit, or theta implicit approach. Okay, so let us discuss the spatial difference. Okay, so you actually have the for the diffusion term, you actually have to calculate this ni cap dot gamma grad phi delta of ai for each and every surface that you have to do. Therefore, if I draw a 2D cell like this, so this one is a y-axis and this one is a x-axis itself, and this one is phase 3 and this one is phase 1 and this one is phase 2 and then kind of this is P, this is A and then kind of this is in cap in and this is theta and uh, this is these are the curvilinear uh, the basis vector along the zeta and the eta direction. So this one is E eta cap and this one is E zeta cap. Okay. So in cap is a normal vector, the vector which is normal to the phase one itself. So therefore we will consider the adjacent control volumes also. And A is the centroid of the adjacent control volume. So A means adjacent control volume. And P is basically my control volume of my. Okay. So now we will consider or we will focus on the cell phase one. We will focus on cell phase one only. And let us call in one cap just in cap, which is in cap is perpendicular to phase one. So E n cap is unit vector along AB and E zeta cap is unit vector along DA. Note n cap is perpendicular to E eta. Okay, but note PA is not perpendicular to AB. Departure from EA being perpendicular to AB is theta, or the angle between PA and AB is theta. I think EA and AB, yes, the departure between not perpendicular. Okay, so the normal vector, the angle between the normal vector, as angle or in cap is at an angle theta with EA. Okay, so let's go to the figure. Yes. So therefore, uh, let's P's coordinate be B XP YP and A's coordinate be xa, ya, and B's coordinate be xb, yd, and A's coordinate be so therefore using the shown xy axis uh, and the O is the origin itself. So this one is a xy axis and this one O is the origin. Okay, and therefore if I draw it further, it will be difficult to make you understand. So this one is basically your A. This is P. This is Q. This is A. This is N. This is zeta. This is along this direction. This is sorry. This is eta and this is zeta. Eta and zeta. And then phase one is basically your this is phase one. So this is A. This is B. This is Y. This is X. This is I cap. This is on phase one. In cap is basically equal to in cap d phi gamma grad of phi multiplied by dA. So this is area of phase one. So this can be like phase one, so which is basically delta A1. So this is equal to, so grad of phi I have to find out. So this becomes what? Either that is d phi dx I cap. So if I actually go for the Cartesian coordinate system, that is d phi dx I cap plus d phi dy k cap. Otherwise, I can write it to be like d phi dn at q. So q is my point over which I am writing it. So Q is basically the intersection between the line AB and also the line PA. So PA is basically the line joining the cell centroid P and cell centroid A, where P is the cell centroid of my interest and A is the adjacent cell centroid. So this is in cap plus d phi dx zeta Q in cap E in cap. Sorry. E eta cap. This is in cap. Okay. So those are mutually perpendicular. So this is your eta and this is your n. So I've expressed it as a function of two orthogonal basis vectors, and then gradient of phi is basically n cap dot gradient of phi, which is basically your how it is written. So gradient of phi is basically d phi dn. Okay, is it clear to all of you? Hello, Pandya Raj, Dhananjay.
Clear, sir. Clear, sir.
एक सेकंड हाँ अभी आवाज क्लियर हेलो अभी मेरा आवाज क्लियर आ रहा था ना हेलो
Yes, yes.
हाँ ठीक है चलो and then now let us pay attention to the shown figure. So d phi d zeta actually represents del dot phi e zeta cap, just like d phi dn equals to del dot phi dot en cap. You should mute your mind, otherwise it's difficult. And d phi d eta equals to del dot phi dot e eta cap. Okay. So now, along PA, different derivative terms can be related as follows. So along PA, derivative terms can be related as follows. तो मैं डायग्राम एक बार प्लॉट कर देता हूँ फिर से. So this is P, this is A, and this is the zeta direction, and this is your eta direction, which is basically the line joining AB, and this is your N, which is perpendicular to eta, and this is basically the N vector is making theta angle with the zeta vector, and this is basically your gradient of phi in this direction. So the gradient of d phi dn actually happens in this direction, which is basically along this in cap direction. If I take the value, the derivative of the scalar field with respect to that of n, and this is basically your d phi d zeta. Okay, so d zeta being parallel to the zeta itself. So let me draw it carefully. Zeta, and this is your cat phi d phi cat phi. So cat phi, and similarly, uh, I'm not fixed. This is P, this is A, this is your zeta cap, this is your eta cap, uh, this is your in cap, this is your d phi d eta, and d phi d in eta, and this is your, if I actually take the projection of it in this direction, so this is cat phi, this is d phi d zeta. Similarly, if I actually put, and then if I actually take it to be this direction, so this will be equal to, this angle is theta, so it will be like d phi d zeta sine theta. Only this portion. So this will be d zeta वो हो गया के बाद ये जो आया, this will be like, sorry, whole thing will be, this thing will be the projection of d phi dn on this line. So it will be like d phi dn cos theta. Okay, and there is another thing which is d phi d eta sine theta. So d phi d eta is basically in this direction. So if I take the projection of this along this direction, so this section will be uh, d phi d zeta sine. Okay, so if I actually correlate all the derivatives, so d phi d zeta will be equal to that of d phi dn cos theta minus of d phi d zeta sine theta, and d phi dn cos theta equals to d phi d zeta plus d phi d eta sine theta, and d phi d eta dn will be equal to d phi d zeta 1 by cos theta. So this you can easily find out by using trigonometry, plus d phi dn tan. Okay. So after that, you can basically write your integral like at phase 1, this will be n cap dot gamma grad phi pa equals to n cap dot gamma grad phi delta a. This will be equal to gamma delta a. d phi dn, and d phi dn can be expressed as a function of d phi d zeta and d phi d eta. So this will be equal to gamma delta a d phi d eta cos theta plus d phi d. So this one, oh, d phi d zeta divided by cos theta plus of d phi d eta tan theta. Okay, so this can be easily written like that, and so uh, that's how you can deal with the convection term. So this d zeta and d eta you have to discretize. So d phi d zeta will be equal to that of phi a minus phi p divided by delta zeta, and d eta will be uh, phi p minus phi a divided by delta eta. Since we already know that if I go to the previous case, so zeta is along the this PA direction and eta is along this small b direction, and that's why it is like phi p minus phi a divided by zeta, and this is phi a minus phi b minus divided by delta eta. So that's why the derivative are being expressed in that manner. So if we actually see this thing, so these are basically second order accurate discretization, central difference thing, second order accurate. So this can be further expressed as uh, gamma delta of a phi a minus phi p divided by delta of zeta 1 by cos theta plus of gamma delta of a phi b minus phi a divided by delta zeta tan theta. So one thing you can, so is it clear until now what I've written, Pandya and Dhananjay?
Yeah, yes, sir. Yes, sir.
Okay. So these things you
Yes, sir.
can,
Clear, sir. Clear.
uh, uh, so, so one thing you can basically see is that I said that theta is basically, I didn't say, but theta is a measure of skewness. Skewness. So if theta is basically equal to 90 degree,
Zeta is representing what term?
theta is basically the angle between the, so this one is basically if I go to the, so theta is the angle between the normal vector of the cell on the phase one. The angle that normal vector is basically making with that of the line which is joining capital P and capital A. So theta is basically the angle between n and zeta.
Then
Zeta,
what is zeta representing? Zeta.
zeta is basically the basis vector along the PA direction. Unit vector which is joining P and A. Okay? You have to look into it. Okay, then you will understand. So if theta is basically equal to 90 degree, then this term actually blows up. Okay. So that I said that sometime in case of unstructured grid, it is kind of difficult to achieve convergence. So theta is basically not equal to so cos theta and tan theta be calculated for each phase and to be stored. So it basically means that these terms we were not storing for that of the structured grid. So this is making the whole thing to be an expensive one. Okay. So this is actually one of the things. So another thing is basically uh, if theta is basically 90, it blows off. And now this is basically this term, the second term which is appearing. This is called the cross diffusion term. Okay, so the cross diffusion term is here. So multiple things should be noted, that A and B are not the locations where phi is solved. Okay. Phi is solved on capital P and capital A. And error which is involved. So thus phi P and phi A are to be found approximately using phi P and phi A. Okay. And other neighboring nodes. This will involve errors. So errors involving error involved in finding phi and phi B using phi P and phi A increases as AB is greater than PA. So this thing you can mathematically check. So the more they are different in size, the more is the angle theta, and more is the angle theta, the error actually increases. So you should be careful while you are dealing with the unstructured grid itself. So this cos theta term, if theta is basically equal to 90 degree, this will blow up and then it leads to divergence. So theta should not be uh, equal to 90 degree. So this is actually one of the things you should look into. So that's how you basically deal with the unstructured grid. So now I'm going to discretize the convection term also. So going to the discretization of convection term. Okay. So control volume P in cap dot rho V phi dA equals to sigma I equals to 1 to 3 ni dot हाँ ठीक है ni dot rho V A sorry phi otherwise I will give a hint on my email ID AI. Okay, so this is how you are dealing with the convection term itself. So now this is basically equal to that of if1 phi 1. So if1 phi 1 if if1 is basically near about equal to in cap dot rho v delta. So this will need some kind of interpolation, but as of now, if we are assuming it to be a constant over the cell phase, the flux over the phase is constant, then we can assume it to be like if1 phi 1. Okay, so details of finding if1 or sorry phi 1, seeing if1 is constant because of conservativeness, it is a constant velocity. And so this one is basically your velocity along this direction is basically constant. Uh, then from there you can basically find out f1. So details of finding phi 1 will depend on the chosen discretizations Digitization. Okay. So sorry, if our point scheme, if our point scheme is used, then for f1 greater than 0, phi1 equal to phi p. For f1 less than 0, phi1 equal to phi a. So if I draw the line itself, so this is K, this is A, this is a line which is joining it, and this is the line which is joining small b and small a. So y-axis, this one is the x-axis, this one is the origin, and this is, sorry, the point B should be upwards, which is point P. This is velocity v vector, which is uh, eta cap, and this is basically zeta cap, and this is n cap. Okay, so therefore, this way it can be done. So depending upon the discretization scheme, you can basically find out the phi1 as a function of, so phi1 can be, it's basically a function of phi p and phi a. And f1, we already know that this is basically rho into u. So if it's a constant velocity, so it will be like rho v bar. So that's why you can basically find out the discretization of the convective term. So therefore, I showed you that how to discretize the convective term, the diffusion term, and also the temporal and the source term itself. So after doing the convection term itself, it is pretty much easy to find out the spatial integration itself. It is very much easy to find out the temporal integration. So that I have showed earlier in the class itself. So I think it is this unstructured grid, this thing I will discuss up till now. And after this, I will start the programming of all the 2 or 3 assignments which are I will discuss my own assignments. I will discuss that how to program it. So is it clear until now? How to discretize the diffusion and the convection term? Hello, am I audible? Hello, Pandya Dhananjay.
Okay, to some extent, I have
Yes, sir.
understood.
Yes, sir. Audible, sir.
Okay. So to some extent you have understood, you should go through the videos once again. You should derive it mathematically. Then you will be understood much more clearly that how these relations came. It is pretty much easy. You can do it. So after this, I will start the programming part. So I will give you an assignment. So I don't know whether, let me search the assignment first. So I will request you to do this assignment. So this is my assignment. So we actually have a domain where, so this is simply the 2D discretization by using the appoint scheme. Okay. So if you are unable to do it, I will supply you the code. That's not an issue, but I want you to try it once. So this is U equals to V equals to 2 meter per second everywhere, so that the velocity field is uniform. So velocity field is not a function of x and y. The sole purpose of assuming it to be, make it simple, uniform and parallel to the diagonal. So it is like a domain like this. It is like a square domain. So this is your x-axis and this is your y-axis. Sorry, uh, this is y-axis, this is x-axis, and this is the origin. And this is the uh, this x diagonal, and this one is basically your solid line. So this diagonal is solid line across the grid. So now the velocities are basically parallel. So this velocity is v, which is the y velocity is 2 meter per second, and u is 2 meter per second, and phi is 100. Sorry, phi is 100, phi is 100, phi is 0, phi is 0. Okay, so the boundary condition are basically Dirichlet boundary condition where the value of the variable at the boundary patch is given, shown. Uh, it is pure convection, so gamma is basically equal to 0. Pure convection, and use affine scheme. Affine scheme in. So this one is basically a spatial convection equation. Okay, so it will be like scheme to discretize the governing equation. Tail dot rho v phi is basically equal to 0. Write a program in Octave, MATLAB, whatever you want, to solve the discretization equation, discretized equation set, equation set. Okay. So therefore, what you should do is basically then you should generate a result like this. So
You are
if
saying it
this
is
is
in octave, what you're saying?
Octave or MATLAB, whatever you want, जहाँ पर भी प्रोग्रामिंग करना है करो, मुझे कोई दिक्कत नहीं है. Octave is basically free version of MATLAB. So distance along x-axis diagonal. So distance along x-axis diagonal. Okay. So here you basically have to plot phi. So phi you have to plot along this capital x-axis diagonal. Okay. Both the analytical and numerical solution, analytical and numerical solution for different grid resolution. Grid resolution. Okay. So the analytical solution, since it's a pure convection problem, so the analytical solution will be typically like this one. So it will be like phi equal to 100 at a certain point itself. So 100 is basically this point, so it will be like 100. So after it crosses a diagonal at this point itself, okay, so it will be drop down and it will go to 0. Since your d phi dx is basically infinity in this point itself, so gamma equal to 0, d phi dx is basically infinity. So that basically means your diffusion is 0. Okay. And numerically, you also have to find it by using affine scheme for differential resolution. That means along the x and the y direction. So this is x direction, this is y direction. You may consider the cell to be like 10 cross 10, 100 cross 100, 1000 cross 1000, and so on. Okay, so I think that this, or you can consider it to be like 10 cross 10, 50 cross 50, and 100 cross 100. Okay, that you have to consider. And then you have to plot it. So you will see for 100 cross 100 itself, it will go certainly like this, 100 cross 100. And for 50 cross 50, it will be like 10 cross 10, it will be like this. Sorry. 10 cross 10. So here we are seeing that d phi dx itself is finite at this point itself, where it should not be. Okay, so d phi dx is 0 at this point, but it is finite when you find it numerically. So this phenomena is basically called false diffusion. So there is no diffusion in the domain since gamma is basically equal to 0, but your affine scheme is basically giving you some false diffusion. Okay, since d phi dx is finite in this region. So this you have to program and then you have to show it to me. You can show the graphs in the next classes. Okay. Otherwise, I will supply you the code.
The red one is 0 by 10 by 10. No,
100 by 100, 10 by 10, and 50 by 50.
no, the
So
red one which you are indicating is in a way 10 by 10. Red
no,
one.
this is not 10. No, red one is basically your analytical solution where there is no numerical diffusion. So this is numerical solution, analytical solution where there is no numerical diffusion. Okay. This 100 by 100 has less numerical diffusion. So this is this part. Okay. So 10 by 10 is having more numerical diffusion. That's why it is more away from the red analytical solution. Okay. So this 2D problem you have to solve by using affine scheme. And you have to show me this graph. In the next class, I will do the coding and show it to you. Okay.
Sir, we have got some email, some clarity is given, but final exam will be consisting of MCQs, objectives, and descriptive questions. What type and what combination, how it is there?
देखो फाइनल क्वेश्चन मैं नहीं कर रहा हूँ प्रोफेसर कर रहा है ठीक है तो फाइनल क्वेश्चन के लिए मैं एक बार पूछ लूंगा बट if certain patterns are written being followed in the previous years those things are to be followed now also ठीक है तो मुझे नहीं पता है कि फाइनल में क्या होगा तो मुझे एक बार पूछना पड़ेगा सर से
Acha, and then I have to receive marks of 2 or 3 assignments as of now. Of course,
हाँ
the assignment 11 is latest, but assignment 9 and I have to receive a couple of them. And I requested for one more assignment to re-evaluate if possible. Because, okay, my numbers are somewhat different from what ideal solution is giving. But out of the 11 details that I asked, for 5 or
हाँ
6, the values are very close. At 3 or 4 places, they are somewhat away. So I requested to re-evaluate and at least consider something. Otherwise, then but difficult for me also. Low score
ठीक है
is difficult. So,
ठीक एक
and
बार
couple of
देख लो वो
assignments are
तो
yet to be assessed. So if you can indicate that assessment, so we'll be able to know how much we are faring and how it can be done.
बात क्या है मैं ये सब चीज नहीं करता हूँ ठीक है वो जो असाइनमेंट का इवेल्युएशन का बात कर रहा है वो मैं नहीं करता हूँ ठीक है मुझे बोला गया है कि मेरा खुद का असाइनमेंट होगा मैं खुद खुद के हिसाब से पढ़ाऊंगा ठीक है तो वो
Achha.
असाइनमेंट के हिसाब से तुम जो मेल कर रहे हो आप जो मेल कर रहे हो दैट शुड व्हाट इफ दे आर नॉट गोइंग फॉर रीइवैल्यूएशन यू कांट डू एनीथिंग अबाउट इट एंड इफ यू हैव एनी प्रॉब्लम रिगार्डिंग द असाइनमेंट एक मेल मैंने शेयर किया ईमेल आईडी तो वहां पर भेज देना देन आई कैन डिस्कस इट इन द नेक्स्ट दैट व्हाट इज टू बी डन एंड व्हाट इज नॉट टू बी डन
हाँ नहीं मतलब अगर असाइनमेंट के लिए रिव्यू के लिए तो who रिव्यूज दैट मतलब री इवैल्यूएट्स को who is doing it कैसा who is the gentleman who is doing
who is doing the professor may give the solution to his students the students may re-evaluate by using the evaluation is done by using the solution which is provided or solution which is discussed between the professor and the TAs itself.
because okay I understand it is not precisely the values which he has shown they are somewhat away from ideal but out of 11 values some 5 or 6 are reasonably close and 3 or 4 places it is somewhat away so that there I can understand but if something can be considered in the assessment so that will be helpful for me also so
हाँ तो वो जाके खुद बात करो वो मैं नहीं कर सकता बिकॉज मैं असाइनमेंट इवेल्युएशन नहीं करता
yeah, but then
मुझे
I am
बोला गया है
we can only write the email so what
हाँ यू कैन राइट द ईमेल्स ईमेल भेज दो उसको बोलो कि प्रॉब्लम हो रहा है यहाँ पर, तो करो, तो उसके हिसाब से वो बता देगा कि क्या प्रॉब्लम है। वैल्यू क्लोज होने से थोड़ी ना होता है, कॉन्सेप्चुअली तुम ठीक हो क्या नहीं वो भी तो इम्पोर्टेंट है। वैल्यू क्लोज होना एक बात होता है, कॉन्सेप्चुअली ठीक होना और एक बात होता है। तो वो किस हिसाब से
हाँ,
करा है मैंने देखा नहीं, तो
आई
मुझे
एग्री।
पता नहीं है।
ठीक है, ठीक।
मुझे पता नहीं है ना, मैं वो सब देख नहीं रहा हूँ, मुझे ऑथोरिटी नहीं है, इसलिए मैं असाइनमेंट तुमसे मांग रहा हूँ। मेरे पास वो एक्सेस नहीं है। मुझे बोला गया है कि खुद का असाइनमेंट फ्लोट करो। तो दिस इज एक्चुअली वन ऑफ द असाइनमेंट दैट आई हैव गिवन टुडे। और तुम्हारा जो प्रॉब्लम हो रहा है मेरा ईमेल आईडी में भेज दो, तो देन वी कैन डिस्कस एंड सॉल्व इट। ठीक है, आई
ओके,
थिंक
ठीक।
वी कैन स्टॉप एज ऑफ नाउ। और ये जो असाइनमेंट दिया है यू कैन ट्राई टू कोड इट, अदरवाइज आई विल प्रोवाइड यू द सॉल्यूशन। ठीक है, ओके।
We have
ठीक
very,
है,
very limited resources of coding, and expertise also very limited, but we are trying to do something. ठीक है, thank you. Thank you.
देखो लिमिटेड सब जगह रहता है, खुद को कोडिंग सीखना पड़ता है। ठीक है, कोई नहीं सिखाएगा कोडिंग। दैट थिंग आई एम सेइंग यू to you. Even in my PhD, I do all the coding itself. You will never find someone who will do both the physics and the coding. ये तो कुछ भी नहीं है कोडिंग सीएफडी का मतलब, इट इज अ फुल फ्लेजेड सॉफ्टवेयर डेवलपमेंट। तो
Okay,
you
ठीक।
have to
Thank you.
find your own ways. Okay, so
Okay,
okay, bye.
ठीक। Thank you. Thank you.
Mhm.